I'm very, very happy to introduce Uli Sattler, who will speak today from word embedding to ontology embedding, preserving meaning and play. Thank you.
Okay, thank you very much for the kind invitation. I'm very happy to be here. I'll tell you in a second. So I am very happy to be in this summer school, and I'm a bit sad to not be in Montreal myself, but I just couldn't make it in the shortness of time, and I didn't want to fly in and out within like 3 days or so. It's a bit too far for that. So I wanted to introduce myself very briefly and just basically take the opportunity to say I've been at UQAM. I've loved being there. I have worked about 30 years ago with François Bergeron, Gilbert Labelle, and it was the coolest time ever I had anywhere. And so I'm really sad that I can't be there with you, but I hope you have a great time in your wonderful summer school and learn a lot about logic and all sorts of related subject areas. I've been working in logic-based knowledge representation, in particular in description logic and modal logics and automated reasoning for a long while. I've been looking into ontology languages and OWL and the underlying logical formalisms, and we have been exploring various ontology engineering tasks, in particular classification, query answering, which you'll learn later today more about, but also explanation and modularity, modular structures, decompositions, and patterns and regularities. So that's just by means of a hello from Manchester to Montreal, and I hope you have a great time. So I was asked to talk a little bit about ontologies and ontology embeddings. And this is what I'm trying to do here in the 45 minutes I have. And we made this title From Word Embeddings to Ontology Embeddings, Preserving Meaning in Space. And I would like to go step by step slowly. And while I can't really explain all of the words used in the title in proper detail, I'll try to give you a bit of a flavor of what they mean and a bit of basic understanding what they are. So, and I'll start with an ontology, and Ian mentioned this a little bit earlier. First, a word of warning, ontology, of course, is a big subject area in philosophy, but this is not the kind of ontology we are talking about here. In computer science, people have borrowed or stolen the term of ontology and just use it as a name for a knowledge base. So in computer science, an ontology is a knowledge base that captures certain domain knowledge. So you pick a subject area like biology, medicine, healthcare, nanomaterials or so, and you capture the knowledge of that domain in an ontology. And then you can use this ontology in an application as some kind of semantic layer, for example, to provide a shared understanding of relevant concepts and their relationships that play a role in this domain. And for example, we can use ontologies to give flexible access to heterogeneous data. And as one of my standard examples, for example, in some databases, you have a specific class of a father. In some other database, you just have people and their sex and the number of their children. And so if you want to retrieve all fathers, you retrieve the explicit fathers from one database, and you retrieve those men who have a child from the other database. If you know what the meaning of father is, or if you have defined the concept of father in your ontologies, in your ontology, then you can do that. So this is the kind of flexible access to heterogeneous data that ontologies give you. And these ontologies are based in logic, and you've just had a very nice overview of logic over the last thousands of years, and got a very good flavor around fragments of first order logic. And here we'll talk about one that's closely related to these. description logics in particular. There are many different ones of those, and there's a funny naming scheme, but we're not going into detail here. And I'll also mention a little bit of the ontology language OWL. But first, let's look into an ontology, and here is a very little toy ontology, and let's see what we find in an ontology. And for 4 decades now, what people are doing is they distinguish 2 kinds of knowledge in an ontology. They distinguish the conceptual part, the terminological part of our ontology from the more factual part. So in our conceptual part of an ontology, we find concepts, relationships between concepts, and relationships between relationships. So for example, we have here concepts such as heart disease and inflammation. In first order logic, you can think of these as unary predicates. Then we have relationships between concepts, like binary concepts, like the specialization or subsumption relationship. Inflammation is a disease, which of course is not a strictly binary relationship. And we have other relationships like is located in. So heart disease is a disease that's located in a heart. And then, of course, we have relationships between relationships like is part of, is transitive, or is located in, transfers through, is part of. And all this is in this conceptual part of our ontology. And then we have this factual part. So factual part is concerns individuals, like here Bob and Beth, and the concepts they belong to or they are an instance of, like here Bob's a person, and of course their relationships, like Bob in this example is a father of Beth. So this is a brief description of an ontology by means of an example. In my example, I have drawn my ontology as a picture, or in particular as a graph. And now, of course, we have to ask ourselves, is that a good idea? Does our ontology fit nicely into a graph? And we could say, oh yeah, pictures are great. They say more than 1,000 words. But I would like to make the case that pictures are not good means to capture domain knowledge. In particular, we need to be a little bit careful with this is a relationship, like heart is a body part and person is a mammal, because there are different kinds of relationships. So the relationship between person and mammal, it's a subsumption relationship or specialization relationship between concepts. That's quite different from Bob being an instance or of type person. And then, of course, we have this funny is located in or is part of relationships. So they are domain-specific relationships, unless you do meronomy. And here, if I draw heart as part of person, you may think, oh, I understand what this means. But then if we poke a little bit deeper, perhaps we are wondering whether this arrow labeled with is part going from heart to person means that is every heart part of some person? Or does it mean that hearts are only parts of persons, or that every person has some heart, or that person only have parts that are hearts? And we may think that in this example it's quite clear, but once I drop heart, person, and is part and replace it with P, Q, and R, it's no longer so clear. And as mentioned earlier, we do this much more nicely in a logic, and this will also scale much better than pictures. So here in our picture we have 8 nodes. Once we have 300,000, it's no longer so pleasant and nice to look at. And we do have ontologies of that size. Good. So what's an alternative to a picture? Of course, logical axioms. And in this case, description logical axioms. And here is an example, but couldn't you have pictures other than directed graphs? Oh yeah, Julia, we could have pictures. And people have tried to make nice, basically to extend Venn diagrams the ones we've just seen in Ian's talk, Venn diagrams with binary relations, etc. But they have come to their limits very quickly, both with respect to expressive power, what they can say in principle, and again with respect to scaling. So the medical ontologies that I have borrowed and abstracted away here in my toy example, the real thing has 300,000 axioms. And a Venn diagram doesn't do work in this case, even when we only take little snippets out of it. Well, they are also, so yeah. I'm happy to discuss this later, but there are good reasons why we want to draw logical axioms. And as we mentioned earlier, these logical axioms are funny ways of basically writing first-order logical axioms, or from a fragment of first-order logic. So when we say inflammations are diseases, we say for all x, if x is an inflammation, then they are disease. When we say that a heart disease is a disease that's located in the heart, we say for every x, if x is a heart disease, if and only if it is a disease, and it has location related to some y that is a heart. We can also have this sort of transitive relation or transferring through between has location and is part of, as depicted here. And then we can do a similar thing with our factual knowledge. So I've extended this a little bit here. Now, Bob is a person who suffers from some inflammation that's located in the endocardium, and we can describe this as a first-order logic sentence in using a constant Bob. So that's where we are with this. Why again? For once, this going from pictures to logic gives us a very nice precise semantics. For example, this set of axioms here entails that endocarditis is a heart disease. So in all models that satisfy all the axioms in our little toy ontology here, we have that every endocarditis is a heart disease. So endocarditis being a heart disease is entailed and can be inferred. If I add that Bob is a person who suffers from an inflammation that's located in the endocardium, I can then also infer that Bob is a patient, and more interestingly, I can infer, or it is entailed, that Bob is a patient who suffers from a heart disease. And that goes back to what I've mentioned earlier about the flexible access to data. I can now ask to give me all patients, I'll get Bob. I can ask to give me everybody who suffers from a heart disease, I also get Bob, despite the fact that it is not explicitly mentioned here. Okay, so I have this precise semantics in terms of these entailments, and I have automated reasoning techniques and tools. So we have seen in Ian's talk earlier how even with already with a few sentences in his from syllogistic logic, reasoning becomes, or determining entailments becomes quite difficult. And so people have developed these automated reasoning techniques, tools, methods, calculi, for example, to classify a given ontology. So classification is one of the core inference tasks here, where we compute the inferred hierarchy of our concepts. And this is a very central task, and the main reason why, for example, people developing these big medical ontologies use logic so that they don't have to place concepts manually in this hierarchy, like an endocarditis under heart disease. They just describe what endocarditis is, and then they press a button, and endocarditis is organized automatically as a heart disease because of its description. That's a very important one. Another one is query answering, and we'll learn later more about this. But so as an example, I can ask a query to retrieve all instances of patients who suffer from heart diseases. Good. So this is my very quick round of through the world of ontologies and meaning in general. So the meaning of an ontology is given in terms of these entailments. And of course, very different ontologies can have the same entailments, and similar looking ontologies can have different entailments. And so this is what we mean by meaning here, entailments. The other thing I need to tell you a little bit more about is OWL. I wanted to tell you about. So OWL is an ontology language, and it's not a logic. It's a W3C recommendation, like HTML or XML. So it was designed for web use, but it's basically, it is on the one hand a standardized syntax for description logics. And a description logic that is quite a bit more expressive than what we have seen in our examples. And to explain that in more depth, or even how the reasoning algorithms would work for OWL, that would go far beyond the scope of this little hour we have here today. But suffices, so it's a fragment of first order logic, but it is much more expressive than what we have seen so far, and it is also orthogonal, incomparable to the syllogistic logic mentioned by Ian earlier. One of the things it has to do as an ontology language, it has to support data types, but we're not going to go much further into this, like integers and strings, because in our ontology, we may want to, for example, define adults as those human beings whose age is 18 or above. So I need the notion of 18 in this sense, or people whose last name begins with an S, etc. So this is not really a logical feature, but an ontology language feature. Another one of those features is related to these annotations. So in my ontology language, not in my logic, but in my ontology language, I can annotate axioms and concepts. I can basically write comments about them, and these comments can be used again by our tools. So I can, for example, say who wrote an axiom and when did they write this axiom, who introduced a term, and most importantly, I can provide labels, synonyms, preferred labels, and labels from different languages for a concept. And because we go to word embeddings in a minute, I would like to just point out here that a term is not a concept. So in my ontology, or in my logical theory, I may have two concepts that share a term. For example, I may have a medic doctor and a doctor as an academic degree, but my medic doctors, they are people, and my academic degrees are degrees that are given by some university. So they're different concepts. And of course, I can have two terms for the same concept. I may have flu and influenza, or flu, influenza, and grippe. I forgot the French word for flu, sorry. And in my ontology, I can make this explicit. So I can have one concept called disease 1, 2, 3. It has a preferred label, influenza, and an alternative label, flu, and things like this are supported by OWL. And then there are quite a few other things. Ian said it's a bit like a piece of software. Oh, no, it wasn't Ian. It was somebody else earlier today. Sorry. We have import mechanisms for modular development and reuse of ontologies. We have versioning mechanisms between ontologies. We have different syntaxes for it, and we have 3 fragments, again called profiles, for efficient reasoning for specific purposes. And we have quite a nice range of tools and reasoners around it. So from this, if you want to take the essence again, you may want to remember that an OWL ontology is a set of logical axioms capturing some domain knowledge, both relating to conceptual knowledge and to factual knowledge. And we can have in an ontology also annotations, labels, and versions. And in case you didn't know, we have hundreds of rich OWL ontologies that are available and widely used for quite a few different domains. For example, in medicine, we have SNOMED-CT and NCI and the human phenotype ontology. We have a very nicely used food ontology called Foodon, and we have quite a few other areas where we have very nice ontology. I should have mentioned the gene ontology there as well. Good. The last thing before I get to embeddings is just for clarification. Now that we know what an OWL ontology is, I would like to clarify what a knowledge graph is. And we'll get to that later today again as well. A knowledge graph, in most people's parlance, relates to the factual part of our ontology. And the knowledge graph is the bit that's easily depicted as a graph, because we mainly have individuals and their types and their relationships. And that's a graph. It's often stored in some kind of triple store or such like, and it's easily shown as a graph and worked over as a graph. So the factual knowledge fits nicely into a graph. Here's a slightly more complicated example. And the one thing I would like to point out here is that if I have such a knowledge graph, people like to do link prediction with it. I like to do first link, what I call link completion. So I want to complete my graph using conceptual part of my ontology. So if I have a conceptual level ontology that works with my graph, like here, I found one, that says that women are persons and dogs are pets and diabetes is a metabolic disease, etc., and has some definitions of dog ownership and pet owners and pet owner spouses, etc., then my knowledge graph, together with my conceptual ontology, entails, for example, that the person called Mary is a pet owner spouse. And this entailment, I don't need to guess it. I know it. Mary is, according to all my domain knowledge there, Mary is a pet owner spouse, and I can just make this explicit in my knowledge graph. But somebody may have forgotten to mention it. I can also, perhaps more interestingly, infer that Mary is at risk of a cardiovascular disease, and I can add that as well. So not all links in a knowledge graph need to be predicted. Some of them can be inferred as well. Right, so I think we are now ready to really go to the embeddings, now that we know what ontologies and meanings are, knowledge graphs, etc. So word embeddings. Where do we start? I'm not going to say very much about word embeddings. They are a mechanism used in natural language processing to capture the meaning of words of some corpus C. So a corpus in this case is a collection of texts. And for my collection of texts, I pick some n-dimensional vector space where n is big enough but not too big. And then I map words or terms from my corpus to some points, and I want to capture the meaning somehow, and I do this by mapping those words to points closely together if they are similar or related. And related in many cases means that they occur in similar contexts. And this has been around for a while. For example, word to vec, so from words to vectors. Vectors are points in an n-dimensional space, are just the same thing. They have been widely and very successfully used to capture meaning of this text corpus. There are different technical details or approaches to them. They've been surprisingly powerful and have been used in early precursors to modern transformers or large language models to capture meaning by proximity, basically, and different directionalities, and have enabled quite interesting for example, analogical reasoning to be expressible in these word embeddings. So these are word embeddings, just points where terms are interpreted as points in some n-dimensional vector space, which is then used further downstream for other machine learning processes. Good. So once we have word embeddings, we can also have knowledge graph embeddings, where we don't start with a text corpus, but with a big knowledge graph, or collection of knowledge graphs, and try to capture the knowledge from that knowledge graph in some n-dimensional vector space. So again, I pick some vector space, and then I may map nodes from my knowledge graph, again, to points in my vector space. And now this is a bit tricky. So in the upper part of my picture, nodes are nodes in a graph, and in the lower one, they look very similar, or yeah, identical nodes. They now stand for vectors or points in an n-dimensional vector space. Now, what do I do with relations? This is where it gets a bit tricky, and people have developed different kind of score functions so that a relation R, so some edge label basically in my knowledge graph, is interpreted as a score function SR that maps 2 points in my n-dimensional vector space to some value. And if that value is below a certain threshold for this relation, then this indicates that the related nodes are R-related. So for example, if I take the vector of Prince Harry and the vector of Prince Charles and the score function of has father, then that score function should score those 2 vectors below the threshold for has father. There have been quite a few such score functions developed, in particular trans-E and node2vec, and they have been proven to be quite powerful to capture the meaning and regularities of a knowledge graph, and are used for link prediction. So, for example, to predict other links that may have been forgotten in my knowledge graph. Okay. So these are knowledge graph embeddings. And the question now arises, what can we see as a good score function? And I would like to mention 2 here, just because they are so important. So trans-E maps basically it scores 2 vectors E and F as the distance of the first one plus the vector of R and F. So it measures the distance of the translation of E by R and F. And if that distance D is small enough, then we say that E and F are R-related. Now, this translational approach, so we translate, we shift the vector E by R to F and then check whether it really reaches F. This only works for functional properties because I only have one vector R associated with my relationship R, and it can only shift one vector to one other vector. So it will not be very appropriate to use trans-E for something like has siblings, because one person can have more than one sibling. An alternative is dist-mult, where I have another vector for my R relationship, and I just take the multiplicative distance between E and F with the weight of R. Now, as you can clearly see from the definition here of dist-mult, this is a symmetric relationship. So now that's quite good if I want to use this core function for my relationship has sibling, because that's a symmetric relationship. If I am a sibling of of Frank, then Frank is a sibling of me. But for sure, it does not work very well for something that is not symmetric, like has mother. My mother doesn't have me as their mother. So there's been a lot of research related to these score functions. Other translation-based score functions have been investigated, and they are all suffering from various from severe restrictions in their expressive power. And it's always the case that if we happen to have a reflexive relation, then it's also transitive and symmetric, which we may not properly want, for example. And they are all such that if two vectors share some R successors, they share all of them. And this makes them clearly unsuitable for likes. So that would mean if two people share one thing they like, they will share all things that they like. And that's simply, not very likely to be the case. And also makes it unsuitable for Isar or type relationships. Good. So what about the concepts? In our knowledge graph so far, we have looked at the nodes, the individuals, and their relationships. What about the concepts? Now, the Isar between concept, the subsumption relationship, is transitive. So if royals are aristocrats and aristocrats are humans, then clearly royals are humans. And of course, if the queen is a royal, then she is also a human. So this interaction with other concept level statements. And it also pertains to being disjoint with. So if humans are not elephants, then then humans being disjoint from elephants also means that aristocrats are disjoint with elephants. And we have got the type instance relationship. It also interacts with these. And we have these other relationships. So this now raises a lot of questions. How do we really want to deal with concepts and these observations and regularities related to concepts? How do we deal with these in our knowledge graph embeddings? And the answer is, well, we don't do knowledge graph embeddings, we do ontology embeddings. And this is where I was aiming for. So, and we try to make use of geometry for these ontology embeddings. So what we do is, again, we pick some vector space, and now rather than mapping all nodes somewhere to some points, I map only individual names, so nodes in my knowledge graphs to points, but I map concept names in my ontology to a region, and I map general regions and general concepts to big regions and smaller, more specialized concept names to smaller regions, like in this example here. Good. So, and I thereby want to exploit geometry in the way, in such that the instance relationship and subsumption relates to or is captured via geometric containment. So here a vehicle, a car is a vehicle, and a vehicle is a purpose-built thing, and pet owners are humans and pets are animals, etc., just because their regions are contained inside each other. And that's the general aim and goal of my ontology embeddings. And once I have this, I can then basically check or measure and talk about the properties of such an embedding V. So I can say I can test whether my embedding is faithful to my ontology. And it shall be faithful if it preserves the meaning of my ontology, and preserving meaning means preserving entailments. So O will entail that E is a C if and only if the vector associated with E is inside the region associated with D. Similarly, my ontology O should entail that C is subsumed by D if and only if the region associated with C is inside the region associated with D. And a similar observation for disjointness. So I can now identify what a good ontology embedding is, what it means for an embedding to be faithful to my knowledge in the knowledge in my ontology. So the question then, of course, arises, which regions? So here I have used n-balls, and they are sort of nice because they are very easily representable. My n-ball is representable by one vector that goes to from the origin of my n-dimensional vector space into the center of the ball, plus a radius, just a value in R. They are easily representable, and then using a bit of geometry, I can easily test whether two such n-balls intersect, or I can compute the union of two, etc. I can also say whether one is inside another one, but what I can't do is I can't talk about houses that are also tens. And this is because n-balls or balls, they are not closed under intersection. So in my example here in the top right, there are things in my geometric model that are both houses and tents, but the things that are both houses and tents don't form an n-ball here, but something that is rather shaped like a lentil. And this poses a little bit of a problem here if my the regions standing for concepts are only possible to express for concept names and not for concept expressions like house and tent. So that's a bit of a problem here. Good. So other people have said, okay, perhaps n-balls aren't great. Perhaps we look at n-boxes or rectangles. And these n-rectangles, they are also easily representable if I make them axis aligned in this way. Then again, all I need is one vector to go to the middle of my box and then an offset vector or to the center. This is why it's called a C, and a second vector that goes from the center of my box to the top right corner. Again, I can use little easy geometry to do intersection, union, etc. And in this case, with these boxes, the intersection again is an n-box, and that is really nice. So the intersection of two concepts is a concept again. That is wonderful. And this is great for concept hierarchies. So just saying patients are humans, diseases are findings. But what happens if I look at richer ontologies like the one we have seen before? What do I need to do to capture these ontologies in geometry again? Well, I need to map relations. And these relations are often mapped to a hyper region, so a region in R to the 2n, and then if I want to say that the relationship R relates E to F, then I just take the two vectors, so the vector of E, stick it in front of the vector to F and check whether, or expect the resulting double long vector to be in the double region associated with my relationship R. And then I can look or test whether my ontology embedding satisfies an axiom like pet owners are humans who own a pet. And in order to do this, my pet owner box needs to be exactly that sub-box of the box of human who are owns related exactly to pets. or into pets. So I have some kind, or I do have a very nice geometric semantics with this. So this is one way of considering geometric ontology embeddings. So I associate a binary with a binary relation. I associate a region in R to the 2n, and then subsumption, for example, like has daughter implies has child, is again inclusion of these regions. And again, we need to ask ourselves, or we need to decide which region to pick. And of course, different choices here come at different computational costs. They provide different logical guarantees, different expressive power. And in general, convex regions can capture certain kinds of ontological axioms. So far we looked at n balls and n boxes. They are, of course, convex regions, but of a special kind. Other famous regions are cones, have been proven to have very good properties, but are a bit tricky in practice. They can capture quite strong decidable fragments. This was a very nice paper by Gutierrez, Basulta, and Schockert. And everything becomes incredibly horrible, or say tricky, once we have more expressive logics, in particular with disjunction, negation, or n-ray disjointness. Okay. My summary so far, since I have to stop very soon. So ontologies can capture factual and background knowledge and terms about individuals, concepts, and relations. In logic with entailments, and these entailments give meaning and semantics. We have these ontology embeddings, where we try to faithfully capture meaning of an ontology used in machine learning models. The geometry really helps if I have concepts and relationships as regions, and inside of my regions as subsumption. We can test or decide, we can design faithful embeddings, and they can be quite tricky in practice. I want to make one side note for those who know first order or modal logic much better. For those who don't, I put a little cartoon here. In owl and description logics, the entailment relates to a statement being true in all the infinitely many models of an ontology O. Now, that can be boiled down to a canonical model in some of our logics, but not in all. But just, of course, an ontology embedding, or any embedding form of my ontology, is just one geometric model, which, even if it's faithful for O, will have to represent all the consequences. And as a consequence of this, I clearly won't be able to do proper reasoning by case or open world semantics. So this is becoming all quite tricky here. Good. So I also don't want to go into very much in detail into applications of ontology embeddings. I would just like to mention that people want to use ontology embeddings for deductive reasoning, which of course requires strong faithfulness, but also raises the question, why not use methods that have been developed straightforward for it? Ontology completion, as this is some kind of inductive reasoning, and there the embeddings really have been shown to capture regularities very nicely, and ontology alignment, where I take two ontologies and try to relate them to each other. Knowledge graphs have been used as knowledge graph embeddings have been used for completion, link prediction successfully. And of course, for downstream machine learning application, our embedding captures domain knowledge. So if I have a rich ontology that I can use, I should be able to use less training, and basically I've been telling my machine learning model already, I've been teaching it my domain knowledge, and these models have been shown then to be very quite well suited for zero or few shot learning for areas where I don't have a lot of learning examples. Good. good. We've done this it's in some older work, and I don't want to go into detail here, other than for the lessons learned. It was really quite cool to inspect our concept embeddings, our geometrical model, and see which, we did use n-balls here, which n-balls are inside which ones. Training was quite difficult. These n-balls are very wasteful. We needed big space. And I want to spend the last minute on another funny ontology embedding, which is called transbox. And just as an example, as a bit of an illustration of another way of embedding EL ontologies, it's a box embedding. We use these vectors as we have seen before, a center and an offset vector. And inside the box of a concept means these are the instances, outside these are the non-instances. We do exactly the same with a relation. So concepts and boxes are translated into relations. And we say that R relates E and F if the vector of E minus the vector of S is inside the box. So it's a kind of translation, at some kind of trans embedding. But now we have a choice. If we make the box a point, we have R a one-to-one mapping. Otherwise, it's a proper many-to-many relationship. And we can capture both conjunction and existential restriction via very simple geometry. And if you can look at those pictures quite quickly, then this will be self-evident. We can do the same with relation composition. We can train them. We don't take them from a reasoner. We can train them. And I've left out quite a few things listed here. And I thank you very much for your attention. And sorry, I can't be there in purpose, but I'm happy to take questions. Hello?
Question in the back.
Do you hear me? Please come.
Yeah, I can. Yeah.
Thank you very much. It was very interesting. I was wondering, regarding everything which has to do with fuzzy embeddings and Gaussian densities.
Can you use a microphone? Sorry, I thought I could hear you, but I can only hear.
So if you stand here,
The microphone is over.
it's right here.
Yeah.
She can see you also.
Exactly.
Right. So thank you very much. I was wondering about your thoughts regarding everything which has to do with fuzzy, flexible, geometric way of evolving, maybe. I don't know how you could call it, your weight measure ontologies. We're having more less or more flexibility without losing the logic and truth. Show us here more transparency in neurosymbolic IA.
So there's a long history of fuzzy ontology languages, and with some very interesting results. And a lot of the time, the fuzzy looking operators were just basically a bit of syntactic sugar, but nothing. So they looked fuzzy, but when it all boiled down to basically normal first order logics. So true fuzzification is really quite tricky and rare. But people have looked into this in detail. I don't know of a lot where it has taken on. A natural point, of course, is this score function, because in this score function, you just have to be close enough to be somewhere. And then you could easily say, hey, if you are a bit close, you're a bit related. If you're very close, you're very related, etc. But yeah, I don't know very much about.
Okay, it could be considered, I mean, in order to capture all the nuances of the language, could it be like maybe a way to explore your models in the future in a way more diverse?
So in these ontologies, we try to have very few nuances. We try to have proper definitions. Yeah, we say, oh, this is a poodle and this is a retriever, etc. Or this is a heart disease and this is a metabolic disease, etc.
Okay, thank you. But in the language we use, there are always nuances, no?
In the language we use, there is fuzzies. People will be more or less tall, but there's also a lot of probability and likelihoods and uncertainty. There are also, yeah.
Many things to say about it. Thank you very much.
Thank you.
Any question? Oh, yeah.
Am I allowed to ask a question?
Yes.
Of course you are.
Uli, it's Ian here. I don't know if you can see me. Can you hear me?
I can hear you, yes.
Okay, I'll shout and I'll come to the microphone if necessary. I'm near the front. But the thing about embeddings in Euclidean space is that Euclidean space has its own geometry.
Yeah.
In particular, according to Helly's theorem, if you have a collection of n convex regions in d-dimensional space, where n is greater than d plus 1, and every d plus 1, every collection of d plus 1 of those regions has a common intersection, then all the regions have common intersection. Right? So
Yes.
so if you have 15 regions in 13-dimensional space, and every collection of 14 of them has a non-empty intersection, then all 15 regions have common intersection. Doesn't this mean that if you are representing concepts as convex regions, and you seem to be, you will have an incorrect logic, because logical truths will be the geometry of the space will impose additional constraints which are not logically consistent. Because it's possible to have collections of 15 concepts, and every 14 of them might have a common point, but there need be no common point to all 15.
Mm-hmm.
I'm about to grasp, yeah. So I think the geometry of the space gives us quite a bit of headaches, and even so I didn't mention this with transbox, depending, so but Ian, how does it, why does it bother us if our logic is infinite in this case? In which sense is it infinite?
You have n-dimensional space. I have n plus 2 concepts.
Yeah.
Statement saying for every set of n plus 1 of them, for all of the n plus 2 sets of n plus 1 of the concepts, for every subset of cardinality n plus 1 of these concepts, I say that there's something satisfying all of these n plus 1, right? So that intersection is non-empty. Now, if that's a convex, if all these things are convex regions, that means all of the n plus 1 elements, subsets of these concepts is non-empty. It follows that your space, the intersection of all of the regions, all n plus 2 of them, must have a point in that space. But it doesn't logically follow that there should be an object common to all concepts. Logically, that's not a valid entailment.
True. And so the lazy answer out would be just make your space bigger. But then, of course, that isn't that isn't the right answer out. We with transbox, we looked at the opposite problem, is where in general, if you take some random boxes in a higher dimensional space, they are very, very likely to not intersect at all. And so all intersections are necessarily empty. So most complex concept expressions will be empty in your embedding. And so getting them together was a little bit, or getting them to be overlapping was a little, or potentially overlapping was the problem. So sorry, no, I don't know.
It's a fair point, but geometrical representations are sometimes tricky.
Yeah.
Other question?
Yeah, so the web.
Yes, we have a question online.
Oh.
Okay, I will.
Question online?
Or do you want to see the chat?
I can see the chat. I just need to carefully focus on it.
Okay, it's Julia's
yeah.
question.
Yeah. Julia's, yeah. Apologies. How does analogy work here? Analogy,
Big question.
so I guess this is still related to the word embedding.
Yeah.
Yes. Because the word embedding trains similarly related people to lie in a similar direction of each other. So it will put the meat to the butcher in the same space as the wood to the carpenter, or in the same direction, because of some happenstance of the training of these algorithms. Are the king and man and queen and women directions? Yes, because the context in which they co-occur between king and man and queen and woman will be similar, and so their embedding will be related in a similar way. Is that the first question, Julia, and does it answer the question? Did you mean, so were you asking about just the word embedding or the ontology or knowledge graph embeddings? So for the knowledge graph embeddings, it's even easier because there we have an explicit geometric interpretation of the relationship. So what are the necessary of the embedding space for the functions you find it? Like we need isotropy. Why does geometry, it seems like a promising. So I'm not really confident that geometry works for ontologies, but people have used, and have used embeddings to capture the meaning of ontologies. And you can put an ontology into a graph. People have done this. I'm not a great fan of it because of various reasons. And then if you use a simple graph embedding where all nodes are points, are embedded as points, you lose a lot of things. The hope here with the ontology embedding and geometry is just that by interpreting concepts as regions, at least you can have geometry to do a little bit of the hard work, and by making more general concepts by embedding more general concepts into bigger regions that contain their more specialized subconcepts, you at least exploit your vector space nicely, and the instance relationship works nicely along the specialization hierarchies, etc. I think this is, I'm a little bit more dubious around geometry than you think there. Okay, I was asking about geometry. So when you think about the butcher and the analogy, so or your example from man to king and woman to queen example, I don't know how to name this relationship. Oh, sorry. there's a simple is-a relationship between them. Yes, so if I say king is to men like queen to what? Then you ask basically a system, what is your next related superclass? And in your space, this is-a should be going in the same direction, and they should come across there.
That's what we call analogy of proportionality.
Okay. In contrast to
Other kinds of analogies.
oh yes.
Yeah, simply.
So the ones for which the word embeddings worked surprisingly, unsurprisingly were basically this kind of relational analogies. I would call them relational analogies, where the relationship between a king and man is the same relationship, but I didn't name it, as queen and what.
Yeah.
Okay. Any more questions?
Actually, yes, one question.
Last one. Okay.
Can you hear me now? Hello, thank you for the presentation. Actually, I'm working on building a legal ontology, which is one of the difficult domains. My question is about, because you mentioned in the presentation the word embeddings and why we need embeddings. So I want to confirm my understanding in terms of the vector representation, because you illustrate a good example once we talk about the function of using or building an ontology. The first one comes as a conclusion because we need to guide and standardize extraction, because ontology provides the domain, vocabulary, allows the concepts, relations, and the categories. The second function for the ontology is to, after extraction, ontology enriches information to support reasoning. So in terms of, my question is about, once we want to talk about legal concepts in general, there is many legal synonyms, many legal vocabulary that seems the same thing in the legal domain. For example, I will give you a real example that I faced lately, which is about, for example, when we talk about privacy policies and terms of use to explain something exists in a legal text. For example, collection, we may collect, we may gather your personal information. So the verb here, the relationship is collect or gather, or keep or preserve. These are synonyms that seems the same meaning, but once we say that we represent them in a vector representation, so I think here is the role to standardize these concepts as one concept. So the machine, when we want to reason, we want to combine ontology with large language model. So the large language model will be guided explicitly that these terminologies looks the same when we want to do kind of reasoning. So just correct me if my understanding about word embeddings as you illustrated in the presentation is the same as I give you now. That's my question.
So, and that's a very good question, and you'll have your work cut out to put a legal ontology together, because legalese is really quite difficult. And I'm just scrolling through because I wanted to get back to this point. So in OWL, and I know I've skipped over this totally. In OWL, we do distinguish between a concept or a property like gathering or collecting, or collection, and its labels, its terms. Yes,
Yeah.
And we'll just have one node in our knowledge graph or one concept in our ontology, and so therefore in our embedding we'll only have one region or one node if it's a word embedding, but we'll have 2 or 3 or 7 different labels with it. Now, if you now go downstream with this and try to tell your large language model that in your concept, these are all synonyms, and please deal with them in this very strictly synonymous way, I'd have to dig deeper and yeah, come back to you on this, how to do that. But this is exactly where the word embeddings and the ontology embeddings would differ, so that we know that we only have this one single concept and we don't have three different terms that just happen to be very closely related in our embedding.
Another question?
Lunchtime? Lunchtime, and we'll be back between 1:15 and 1:30, Marianne? Okay, and we start. Okay, and we start exactly at 1:30. Thanks to our speakers. Thanks.
Thank you. See you later.
Thanks to you.